Hello everybody and welcome to Module 4. We are getting into inferential statistics this time. We are going to be talking about hypothesis testing, and before we get to hypothesis testing or our inferences about a population based on sample data and answering interesting questions or testing predictions, I wanted to talk about sampling distributions, because before we can really talk about how we do our hypothesis testing, you need to have an understanding of what it is exactly that we do to use that process. And sampling distributions as a mean are not difficult once you see them, but seeing it helps a lot. Okay, so when we're doing inferential statistics, we are, as I said, generalizing from a sample to a population, not like an external validity. We are taking a sample and we are testing it. And we are saying that what's true of the sample is probably true of the population. And we want to see just how likely that is. And if we're looking at likelihoods, we're talking about probabilities. But before we get to probabilities, let me go ahead and talk about sampling distributions. First of all, if you remember, we talked about the natural deviation or difference between a sample mean or standard deviation, a sample statistic, and population parameters like mu or the standard deviation sigma. There's always going to be that natural difference. And the sampling error is not something that's wrong or a mistake, it is simply that natural difference. And samples vary, so no two samples are going to be identical or exactly alike, so therefore you're going to get a bunch of sample means. So think about, say you have thousands of people, hundreds of thousands of people, and you have a sample over here, and you have a sample over here, and you have a sample over here, and say you do 3 different studies on the same thing, or 3 different researchers do the same study to kind of get some generalization. You're still, even if you've got a population of depressed people and you've got depression scores for all those individuals, this sample mean is probably not going to be equal to this sample mean. And it probably won't, this one probably won't be equal to the other two either. Now, you might, accidentally get means that match, but the standard deviation probably won't match. So there are going to be some differences. All samples are slightly different. And usually they differ, like I said, through, naturally through this sampling error from the population mean. So we have to kind of look at the relationship between our population parameters and our sample statistics. So when I want to talk about the distribution of sample means, basically it's the collection of means for all possible random samples that can be obtained from a population. So what I've done here is I've created a population of scores, 2, 4, 6, and 8, and you imagine that normally we have populations of hundreds of thousands of people, and we have a sample maybe of 100 or 150 or 55 or something. But here, just to keep it simple, and you'll see already that it gets a little bit more complicated, we have 4 scores. Those are all the possible scores that we have in our population. This is our population of scores, and therefore this would have a mean of mu. And that would be, our mu would be our average, or our mean, so we would add these together and get 20 and divide by 4, and our mean is 5. So mu here is 5. Now keep that in mind, because what we're going to do is we're going to take samples of size n equals 2, so 2 samples of size 2, like if you were to have 2 individuals complete your survey or something. Here we're going to draw an individual, a score, and then we're going to put it back. If you remember, one of the assumptions of random sampling is sampling with replacement, and we talked a little bit about how we don't reuse our participants, but that's still an assumption underlying the distributions that we use to make decisions. So we take and we draw from here, and we would randomly draw, but in this case I'm going to walk you through the possibilities so that they make sense. So first, you could draw a 2, and of course you put it back with replacement, and you could draw a 2 again. You could draw a 2 the first time and then draw a 4 the second time, giving you this sample. You could draw a 2 and then a 6, and so on. You could maybe draw a 4 first and then a 2, a 4 and then a 4 and a 6, or a 4 and an 8, etc. And that's what I've done here, is I've laid out all the possible ways that these 4 scores can be sampled in groups of 2. That's what this is. And so what I've done here in these columns is I've added the numbers together. 2 plus 2 is 4, divided by 2 is 2. So I now have the mean of each sample. So here, we've got a total of 6 divided by 2 is 3, and here 8 divided by 2 is 4, etc. And you'll notice that the means Some of them are very infrequent, and some of them are more typical. They happen more times. And so this is your distribution of the means. These are the possible means that you can get with all samples of a certain size n. So what I've done here is I've used descriptive statistics to make a frequency distribution so you can see how frequently the means happen. And I've also graphed it for you down here. So here we have the mean of 2, and it only happens once, because the only way that you can get a mean of 2 is to draw 2 twice, and that's the lowest score, and therefore the lowest mean. And then we have 8, which also happens once, because 8 is the highest score, and you can only draw that twice, and so that's as high a mean as you can get. So 1 and 8 are very uncommon scores compared to, you get 2 3s, 3 4s, and then you get 4 5s, 3 6s, and 2 7s. And what's interesting to note here is our mode, which is 5, is where the scores are piling up. You can see it here in the picture. There are more sample means that have a mean of 5 than any other mean, and that matches our population mean. So that's one of the rules, is that our sample means are, as we take the distribution of sample means, they're going to pile up around the population mean. They're not going to all be the same, but we're going to get some of them. If we take all these possible combinations, we are going to get many of them close to the mean. So it's easy to get a sample mean that's close to the mean or at the mean. They're the most frequent scores. But as you see, there are also some outlying scores with our 2s and our 8s. Okay, so the sample means pile up around the population mean. Here it's 5. And another thing to notice is that this looks like a normal distribution. It's actually perfectly normal. It's because of the numbers that I chose. And if you start off with numbers that are normally distributed, you will get a normal distribution when you do a sampling distribution of the means, or get the distribution of sample means. The other way that you can get a normal distribution, roughly, is to have a size of about n equals 30. So instead of our little 2 here, taking 2, we would take 30. We don't even have enough scores. But if we had, hundreds of thousands of people, and we took 30 at a time, as we had a larger sample size, the central limit theorem says that 30 is kind of our magic number. But as we get bigger, as we have more and more participants or individuals in our sample, we approach a truly normal distribution. So that's all I really need you to know about the central limit theorem. It says that basically any population with mean of mu and standard deviation of sigma should have the distribution of sample means will then, of any size n, will then have a standard deviation of, write it down, a mean of mu, because it will approach the population mean. It will become the expected value, because we expect the mean of all of these numbers to be the same as the population mean, or the mean of all our means to be the population mean. It will have a mean of mu and a standard deviation of sigma divided by the square root of n. So our sampling distribution of the means, or our distribution of sample means of any size, will have a population mean, will have a sample mean the same mean as the population, and it will have a standard deviation slightly correcting for that sampling error that we always have, because it's not going to be perfect. Okay, so hopefully you understand this. Now what we can do is, once we have this all these possible combinations of sample means, then we're going to take our mean, say that we get from our sample, and we're going to compare it. We're going to see, well, how likely is it that it would fall along this continuum somewhere? Is it out in the outlying areas? Is it a more central score? You kind of see where this is going in terms of z-scores, hopefully. The farther out in the distribution it is, the more extreme it is, and the less likely that it just occurred by chance, because, well, here, it was inevitable that it was going to happen. It was one of the possibilities. But what we're going to do is we're going to use the same idea where other people have taken sampling distributions of means of z-scores, and then they will use that normal distribution, and they will then find the exact probability. What is the exact probability of getting an 8 out here, or a 2, as opposed to a 4, or 5, or a 6. It would be much easier, a much higher probability of getting a more central score than a more peripheral outlying score. So that's where we're going with the sampling distribution of the means. Once you understand that that's what we're doing, we're going to start doing this with all kinds of samples. We're going to, or all kinds of different statistics. So we'll do one of these called the null hypothesis distribution, where we take a theoretical sampling distribution of all the possible means that we would get if we ran an experiment that was completely unsuccessful. If the treatment did not work, we would still get a normal distribution, and we would still get, most people scoring close to the mean, close to the zero that we would expect. There's no treatment effect. But you would get a few people out there who would actually score higher or lower, and they would be out in the tails of the distribution. So we're going to compare our statistic that we calculate from our sample, and we're going to compare it to the population. We're going to say, where is that along that continuum? Is it extreme enough for us to say that's probably not a chance finding, or is it just too central and too typical a score, and we just don't feel confident enough to say that our sample is significantly different from the population? And that's basically the first part of what we're talking about with hypothesis testing. Hopefully that was followable. Hopefully you guys can see it, and I will be back to talk to you guys about the decisions that we make with hypothesis testing and a few other things as well. And we will begin with z-scores, because you guys know and love them from before, and we will hopefully any questions that you have address in class. So do bring questions about this, the sampling error, sampling distribution of mean, any of those things. Bring them to class, and hopefully this was helpful. All right, see you guys.